Hey, good afternoon, everybody. Thank you again for coming to the Origins seminar. Today we have a talk by Leon Trapman, who did his PhD at Leiden University together with Michiel Hogerheide on the modeling and observations of protoplanetary disks, and specifically trying to figure out how to measure the sizes of protoplanetary disks. After his PhD that he got in last November, he has moved to the University of Wisconsin and is now working there, also on protoplanetary disks. And today he will give a talk at the Origins seminar. As a short reminder, try to keep your videos off to save bandwidth for the people that don't have super stable internet. And if you have urgent questions, please put them in the chat. Then we, as organizers, will ask the question, and less urgent questions, please keep them to the end of the talk. So now I would be happy to give the floor to Leon to give his talk.
Yeah, thank you, Sebastian. Thank you all for coming to my talk and give me the opportunity to present some of my work here. Well, as you can guess from the title, we're going to talk about protoplanetary disks, and we're going to talk about those the sizes of protoplanetary disks and what they can tell us about them. But let me start with going sort of one step back and say a few words about why we're actually interested in protoplanetary disks. And the main reason is we want to understand planet formation. We know from all observations of planetary systems that they come in a wide variety of different compositions and sort of planets that can be found in them. So on the one end of this scale, as you can imagine, there's a system like TRAPPIST-1, where you have a lot of rocky planets all packed very close to their star. And then if you go to the entire other end of the spectrum of planetary systems, you might find a system like HR 8799, which has multiple gas giants at orbits of tens of AUs around the star. So there's a variety of planets and planetary systems. So the question then is, how did they form? And also, why did they form so differently? And to answer that, let's go to this sort of overview of star and planet formation. I think many of you will be familiar with a figure like this, which just sort of describes the different steps of star and planet formation. So thinking back to what I just showed, if we want to know more about the planetary systems, which are at the end of this track, what we actually want to know, if we want to know how they formed, we want to go sort of one step back and go to the protoplanetary disks in which these planets form and grow. So to give you a little bit background of protoplanetary disks, which will be the main topic of this talk, most of the material in these disks is gas. And that gas is mostly molecular hydrogen. We think about 1% by mass of these disks. It's composed of dust grains, which can grow up to millimeter sizes and maybe larger. They have to get to planets at some point. The material in these disks is also cold. The typical temperatures around the midplane of maybe even lower than 20 Kelvin, between 20 and 40 Kelvin. And these disks stay around for about 1 to 10 megayears. And most importantly for us, of course, inside these disks, planets are being formed. If we want to observe these disks and know more about them, we usually like to go to ALMA, which is because these disks are, like I said, very cold. That means that they're very bright at millimeter wavelengths. So at millimeter wavelengths, we can get the continuum emission of the millimeter-sized grains that are found in these disks. And we also get a wide range of molecular line emission from the most common molecules in these disks. And the reason that we like to go to ALMA is ALMA has both the resolution and also the sensitivity to help us study these disks in detail. Now, if you're thinking of ALMA observations, one of the first things you might be thinking of is these images on the left, which is the very high resolution observations of D-sharp, in this case of the continuum emission, showing all these nice substructures, rings, gaps, spirals. So that really helps us to study individual disks in high detail. But that's not the only thing that ALMA can do. One of the other things that ALMA can do is what we call disk surveys, where instead of going very deep on individual sources, we just go for very short, 1 to a few minute snapshots of each disk in a given star forming region, like lupus that I'm showing here. So what can we learn from these disk surveys? I'm showing here some sort of a gallery of the both the continuum and the CO emission from one of these surveys. As you can see, the resolution is not at the same level and the sensitivity is not the same level of D-sharp, so we don't get these very high resolution images, but instead we get a large range of from observations from which we can measure the bulk properties of these disks. Things like the dust mass from the continuum emission, the gas mass from optically thin 13CO and C18O line emission observations, although there are some caveats there linking those to the total gas mass, and also things like the size of the disk, which is what I'm going to be focusing on here. And because we have these observations for all disks in a given star forming region, we can also say something about the population. We can make figures like you're seeing here on the bottom right of the slides that you might have been familiar with, which is just sort of showing you what fraction of disks have a disk, in this case, a dust mass larger than the value on the x-axis. And that really helps you to show you that there's only a fraction, or it helps you to show that there's maybe only a fraction of disks at the, let's say, 1 to 2 or 2 and older mega years that are still have enough dust mass to actually form the cores of giant planets. So that tells you something about how and when planet formation needs to start. So armed with these observations, what are the sort of the kind of questions that we want to answer, and what we're also going to look into in this talk. So the first one is, how does the dust evolve? We know that it starts out at sub-millimeter grains in the ISM, and it needs to grow at least 13 orders of magnitude to get to planets, which are the things like the end product that we're interested in. How does it do that? One of the other questions is, how does the gas evolve? The gas makes up most of the material in the disk, so how the gas is evolving is going to dictate how the disk is evolving and also how long it stays around. So is this evolution occurring, for example, very turbulent, which is sort of the picture for viscous evolution that I come back to later in the talk, or is it happening very quiescent, and is it maybe driven by disk winds? That difference between turbulent and quiescent also has an impact on how easy grains can grow. And it turns out that the sizes of protoplanetary disks can actually help us answer these questions. So let's go to the first one. How does the dust evolve? Well, before we're going into that, let's first look at, actually take one step back and look at what does the size of a disk mean. So what I'm showing here is 2 observations of the same disk. On the left showing the CO rotational emission, which is tracing the cold molecular gas. And on the right, I'm showing the 0.87 millimeter continuum emission, which is tracing sort of the millimeter sized grains. And as you can see, if we're talking about size, it looks like that what we define as the size of the disk is going to depend on what we're using here, because the CO disk is much more extended, or at least the emission from the CO disk is much more extended than the emission from the continuum disk. So why is this happening? Before I dive into that, let me briefly give you a definition. Whenever I'm going to be talking about size of a disk in this talk, I define the size of the disk as the radius that encloses 90% of the flux. So if I'm talking about the gas disk size, I'm talking about the radius that encloses 90% of the CO 2-to-1 flux in this case. And when I'm talking about the size of the dust, I'm talking about the radius that encloses 90% of the millimeter flux. So keep those definitions in mind when we're talking about sizes here. So why are we seeing a difference in size between the CO emission and the continuum emission? Well, one explanation is linked to grain growth and radial drifts. So the grains in these disks grow from the small ISM sizes to sort of millimeter sizes, at which point they start to decouple from the gas. And as they decouple, they start to feel a headwind from the slightly slower moving gas, and they start to radially drift inwards. Well, that sort of matches what we saw in the observations, because radial drift of these larger grains would mean that while the gas stays behind, all of the millimeter grains have moved inward towards the star. Hence, we're seeing a more compact disk of continuum emission compared to the CO disk. That's, however, not the only way we can explain the observations. The other way is through optical depth. Because we measure like I said, we measure the dust from the continuum emission, which is mostly optically thin at millimeter wavelengths. However, we're measuring our gas from the 12CO emission, which is mostly optically thick in disks. So that means that for the same amount of sensitivity, we'll be able to see the CO to much larger radii, even if the gas and the millimeter grains are following the same surface density profile. So which of the two actually explains the observations? Which of the two is more important? Well, to answer that question, we're going to go to models. And in my case, that means going to DALI, which is a thermochemical model, which I like to think of or like to explain as a protoplanetary disk in a box. So basically, you give it a description of the surface density and the star inside the disk, and then it starts to calculate the temperature. It calculates the chemistry. It calculates the excitation of the different molecules, and then in the end, you can ray trace your model and get observables like, for example, the continuum emission and the CO emission that I showed previously. Now, because this is a model, we have full control of what we actually put in and don't put in our models. So if we use the standard version of DALI, there is no radial drift included in there. So if we put in a surface density structure of a disk and we run the code, then at the end we will get both the gas disk size and the dust disk size from synthetic observations that doesn't have any effects of radial drift in there. The only effects that will be in there are the effects from optical depth, which are included in the code. This we can then compare to a sort of a variant of DALI, which actually does include dust evolution. So this is a version of the code developed by Stefano Faccini that actually included dust evolution. So if we now put in our same density structure of our disk, run the code again with this different version, and look at the synthetic observations, we'll now have both the gas disk size and the dust disk size of the combined effect of optical depth and dust evolution. So by comparing the two, we can actually compare these or relate these two things in our observations and learn something about them. So that's what we did. So what I'm showing here is a figure of the difference in size. So our gas over our dust as a function of disk mass, which turns out to be one of the most important parameters in changing this ratio. And I'm starting off with showing you the models that didn't include any dust evolution. And as you can see here, as we go to higher mass, the ratio between the two increases because a larger part of your disk is optically thick, and therefore the apparent size of your gas disk becomes larger, up to about a ratio of, let's say, 3.6. If we now want to compare that to the same models, but those that include this evolution, then you get this. The colored lines here are models with dust evolution included, where the different colors indicate the amount of turbulence. With a high turbulence, as a reminder, means that grains will be able to fragment easier. So a higher amount of turbulence sort of suppresses the growth of grains. As you can see here, if we compare the models with and the models without dust evolution to each other, the models with dust evolution have a larger R gas over R dust, which is completely what we expect because they have both the effect of optical depth and also dust evolution. And it seems that if we sort of draw a line at a difference of 4, we can sort of separate the two. So if we're finding disks that have our gas over our dust that is larger than 4, we can be sure that these have undergone dust evolution. These have undergone radial drift. The grains have moved inward, and that's what we're seeing in the observations. However, if we have a difference that is smaller than this, then both are still an option. So this seems like quite a large number. So are we actually seeing these in observations? Well, it turns out, yes, we are. These are observations of the disk CX tau by Stefano Facchini, where they found a gas disk that is about 5 times larger than the dust disk. As you can see the CO on the right and the continuum on the left, there's a massive difference between the two. So for this disk like these, we can be sure that they have undergone radial drift. However, this of course is a very neat example, but in most cases, it's not that clear. In most cases, especially, I'm showing here observations from the Lupus disk survey. It's not as clear, also because 1 minute of integration doesn't give you a lot of signal to noise. So it's sometimes hard to see what is actually going on in here. So if we look if we look at all of the disks in Lupus and we look at their gas disk sizes and their dust disk sizes, what are we finding in terms of the difference in between our gas and our dust? Actually, I used to give this talk with a different figure here, but recently there was a reanalysis by Enrico Sanchez of the data in Lupus, where they were able to get a lot more gas disk size measurements out of the data, and we're actually finding a number of disks that have a ratio larger than 4. So if you imagine this green line as the same cutoff that I showed in my models figure, there's about 5 disks that are above there. So there are a few in there, but the majority of them actually have a ratio that is closer to 2. So a gas disk is about twice as large as the dust disk. So what can we say about those? Well, we can assume that the only thing that for these disks that we're seeing is optical depth effects, because they didn't have this large difference. So let's assume it's just all optical depth. To dive a little bit deeper in there and see if that still makes sense, what we did is for a subsample of these disks, about 10 sources, we actually we made a model that fit the continuum, and we put that into DALI, the version without dust evolution. If we're right that there's only optical depth for what we're seeing here in terms of the gas disk size, we should reproduce the difference in size between the two, because the dust should have the same surface density, follow the same surface density as the gas. So we're able to sort of reproduce the observations based on that. When we do this, we find that there's, of the 10 sources that we looked at, there's actually 5 sources that are shown here in black that match the observations within the uncertainties of the observations. So for these sources, it seems like optical depth can explain our gas over our dust that is observed. However, there's also 5 sources that if you model the source individually, you find that the model that only has optical depth produces a smaller difference in smaller R gas over R dust than what is observed. So for these sources, we need to add something. Optical depth is not enough. So it seems logical that for these sources, we need to add dust evolution to actually match the R gas and R dust that are being observed. Of course, what you can also see in here, especially for the black sources, these are very large error bars. So the quality of the data is also definitely playing a role here. But based on the current observations, this is all that we can say here. So summarizing everything that I told about the dust and the gas, or sorry, not the gas, that's next. The dust, we found that our gas over our dust, the difference in size between the gas and the dust, If it's larger than 4, that seems to be a smoking gun for dust evolution. That's clear evidence that we're seeing dust evolution in these sources. If the ratio is smaller than that, we cannot be certain just based on the sizes. We need to do more work. And of the 10 sources in Lupus where we actually modeled the individual sources, we found that if we do that, then 5 of them still need to add, we need to add dust evolution to match the observations. But for the other 5, optical depth seemed to be enough to explain what we're seeing here. So that's it for the dust. How about the evolution of the gas? Well, for that, you can ask, what drives the evolution of the gas? Well, a protoplanetary disk, at its core, it's an accretion disk. So material is moving through the disk and is being accreted onto the star at the center. However, to drive that accretion, you need to do something with the angular momentum. The angular momentum of the total system needs to be conserved. So to drive the accretion, you either have to move your angular momentum outwards, or you have to find some way of removing it completely from your disk. So the first idea is that, which is called viscous evolution, where viscous stresses and turbulence in your disk are sort of moving the angular momentum outward, making a small amount of mass at the outer part of the disk move outward and take away all of the angular momentum, which then in turn drives most of the mass inward and allows it to be accreted onto the star. However, there's another way of driving the accretion, which is through MHD disk winds. These disk winds, magnetic fields in the disk, allow you to launch material from the surface of the disk that then sort of carry away the angular momentum. And because angular momentum is being removed from the disk, material is driven inward and is accreted onto the star. So how can we differentiate between the two? Well, again, we can turn to disk sizes, because if it's viscous stresses and turbulence, if it's viscous evolution that is driving the evolution of disks, then disks should grow over time. That is the way that viscous evolution works. However, if it's disk winds, then there's no reason for these disks to grow over time. They should stay the same size. So that is something that we can test. We can look at the sizes, the gas disk sizes of disk as a function of time, and use that as a way to distinguish between disk winds and viscous evolution. That is something that people actually looked at, including Najita and Bergen quite recently. They collected a sample of disk sizes from the literature of both the younger, still embedded class 1 and class 0 disks, and also the larger, or not, the older class 2 protoplanetary disks. And from comparing these two, there seems to be a trend for the older disks to be larger than the younger disks. However, they were limited by the data that was available. These literature disk sizes are often using different tracers and different definitions of the size. So we wanted to go back to the models again and see, okay, how well is, if we take our definition of the size, the 90% of the flux, how well does that trace viscous evolution? Is that a reliable tracer that we can use for this? And also, if we compare sort of the size based on observations from our models to the actual observations, what can that actually tell us about the viscous evolution, if it's there? What kind of amount of viscosity do we need to match the observations? So to go a little bit into the way we set that up, because we in the end wanted to compare our models to the observations, we wanted to pick our starting point also in some way matching the observations. Well, for a viscous disk, you can write down the equations and you can find that the initial mass of the disk is related to the accretion time, the stellar accretion rate at a given time, and the sort of the viscous time scale, the time scale over which disks evolve. And the viscous time scale is related to how much turbulence there is in your disks. So for Lupus, we actually have the stellar accretion rates. So what we did is we picked 3 stellar accretion rates that sort of correspond to the average accretion rates of stars with 0.1, 0.3, and 1 solar masses. And we use those accretion rates. And then for the different amount of turbulence, we calculate, okay, given that accretion rate and this amount of turbulence, what is the initial disk mass? What must the initial disk mass have been to actually match the observed accretion rates? And that then gives you your initial mass. Because DALI is not a sort of a dynamic code, it doesn't do surface density as a function of time, really. You need to pick a time. So what we did as a workaround is for different times between 0.1 and 10 megayears, we calculate what the disk mass must have been given the accretion rate and the amount of turbulence, and also what the size must have been given those same things. And then for those conditions, we run a DALI model to get synthetic observations of our given disk at that time. Now, the one thing I haven't talked in this is the initial size. We chose to pick an initial size of 10 AU, a characteristic radius of 10 AU, which is something that I'll come back to later when I show the results. So based on our models, this is sort of the thing that we can now make. So I'm showing one model here, in this case, a disk around a 0.1 solar mass star, which for giving our setup has an initial disk mass of about 10 to the minus 4 solar masses. And then on the left, I'm going to show the evolution for a high amount of turbulence, so where the disk goes very quickly. And on the right, I'm going to show the same disk growing under a very low amount of turbulence, so where the disk will grow very slowly. And what I'm showing is the 12CO intensity profile, from which we're going to measure the gas disk size. And also, because we're interested in the gas disk size, I'm including this cross here at the bottom of each of the panels, which actually shows the radius that encloses 90% of the flux, so our gas disk size. So this is for 0.1 megayear. If we go to 0.5 megayears, you can see that indeed the model with the high turbulence is growing very quickly. Also, the 12CO intensity profile is growing very quickly, whereas for the low turbulence one, you don't see much change. The disk hasn't really evolved much between these two time steps. We can sort of continue that up to about 2 megayears, and then I want to draw your attention to what the observed size is doing for our high turbulence case, because at 2 megayears, after 2 megayears, it starts to decrease in size, reaching about the same size at 10 megayears that it was at 0.1 megayears. So what's happening here is that this disk is sort of becoming the victim of its own success. The surface density is increasing, is sort of, as the disk expands, the surface density in the outer disk is dropping, meaning that UV photons now have the opportunity to actually penetrate into the disk and photodissociate CO, removing it from the gas. So that the thing that we're using to measure the size of the disk is being removed from large parts of the disk. Hence, the observed outer radius is shrinking over time. Now, of course, or not of course, I'm showing you one example here, the example that is different from the rest, because this behavior of the disk, the observed size growing over time and then starting to shrink, is only happening for our disk model which has the lowest initial disk mass and has a high turbulence. That is the only one where we're seeing this. For all of the other ones, it seems that the observed size is a good tracer of the viscous expansion of the disk. So if it's growing over time, and if the turbulence is higher, then it grows quicker compared to the same model with a lower amount of turbulence. So let's compare what we're seeing in the observations, or what we're seeing here in our models, to what we actually see in the observations. So here I'm showing observed gas disk size as a function of time, and I'm showing two sets of observations in here. In black, I'm showing disks in lupus, for which we have the gas disk size measured with the same definition as we use for our models. And in purple, I'm showing disks in upper SCO, which is a much older region. Lupus is about between 1 and 3 megayears, and upper SCO is between 5 and 10 megayears old. As you can see here, between comparing the observations to the models, it seems that the disks, at least in lupus, are consistent with being viscous disks that have evolved with a moderate to low amount of turbulence. Turbulence, or an alpha of 10 to the minus 3, is sort of the highest that still matches with the observations, except for the two very large disks that we're finding here in lupus. They do have difficulty explaining the disk in upper SCO. It's very hard for our models to get to the small disk sizes that are measured in upper SCO. So that's something to think about. This could be photoevaporation, external photoevaporation. We know that upper SCO is a star-forming region that is very close to the nearby SCO-SEN-OB association. So there are a lot of O and B stars in the environment of these disks. So maybe they have sort of removed material from these disks, keeping them smaller compared to the disks in lupus. So that could be an explanation. I mentioned that I was also going to come back to the initial size. So it turns out we actually tried starting our models with a larger initial size, but we found that very quickly they become much larger than what is being observed. If we go from an initial size from 10 AU to 30 AU, we're already larger than most of the disks that we're seeing in lupus, and definitely larger than all of the disks that we're seeing in upper SCO. So the disks in lupus seem to be consistent with viscously evolving disks that have started small and have evolved with a moderate to low amount of turbulence. So I'm saying here consistent with, because this is not evidence that there actually are viscously evolving. So in the last few minutes, let's actually go to the other explanation. How about MHD disk winds? What do we expect in terms of observed size evolution for these disks? And also, how does that match with observations? Well, if we want to investigate that, we're going to need a model, and that means going back to sort of the evolution equation for the surface density in disks. Don't be too worried about the equation here. I'm not going to go into much detail here, but it's sort of the first part of this you have already seen. This is sort of the angular momentum that is extracted radially through viscous stresses. That is sort of the first part. That is the surface density that you saw previously for the viscous models. If we want to go to wind models, or if we want to include MHD disk winds, we also need to include a term for angular momentum that is being extracted by the disk wind, and also this same with disk wind is also removing mass from the disk. So we need to include a massless term in here as well. And then I say we, but actually I'm using all of the equations and the derivation here are from Benoit Tabon's work, also from Leiden, which is what they did is similar to what we did for the viscous model. We're going to define a alpha parameter that is sort of incorporating the strength of how well these winds are able to remove angular momentum from the disk and thus drive the accretion onto the star. Now, the difference being that apart from an alpha that we need to introduce, we also need to introduce a second parameter that sort of tells us how efficient the wind can extract angular momentum from the disk. If this number is very low, that means that we need to remove a lot of mass from the disk. Am I saying that correctly? I think so. we need to remove a lot of mass from the disk to drive the same amount of accretion. Now, of course, this model is the most general case where you have both viscous evolution and also disk winds. What I'm going to show you here is just only the disk wind part. So I'm setting the viscous alpha to 0, and I'm only going to look at this part. So let's show you how the surface density looks comparing a wind-driven model to a viscous model. So these models both have the same initial conditions, and what I'm showing here is how the surface density changes as a function of time with the different colors. And then you can see there's sort of two main differences between the two surface density profiles. The first one is that in the inner disk, sort of this power law part of the surface density, for a wind-driven model, that is a much flatter slope compared to the viscous model. And the reason for that is as material is being transported inward, the wind continuously is moving material from that parcel of gas that is moving inwards, so that process sort of flattens the slope in the inner disk. You can also see that, I should mention that I have included RC, so the size that goes into your surface density. For a wind model, as we expect, it doesn't change over time. For the viscous model, this is growing over time. And the other difference that you see between the wind-driven and the viscous case is that the disk mass increases faster for a wind-driven case, because it has both the accretion onto the star that is sort of draining the disk, but it also has the wind that is removing material from the disk. And the combined process of the two sort of increases how quickly the disk mass decreases over time. Now, of course, we're also interested in the surface density, but what we're mostly interested in terms of getting to the observed size is, again, the CO intensity profile. So I'm showing CO intensity profiles for both the wind-driven and the viscous case. Again, with going from red to blue, going from young ages to old ages. The way that I've set up the disk wind model is very similar to how I've set up the viscous model here. The viscous model, I mean, I've showed it before. It starts out small, and then as the disk expands, the CO intensity profile sort of expands outward at the same in the same way. The wind-driven case, it's the opposite. It starts out quite large, but that is just me setting the initial conditions as being quite large, and then over time it starts to decrease, because as the total amount of mass in the disk decreases, the column densities decrease. So larger parts of the outer disk are now at such low density, similar to what I showed for the viscous model, are at low density that CO can be photodissociated in the outer disk. So the region of the disk that can contain CO is starting to shrink over time. So that means that if we plot the size as a function of time, we can see that for a wind-driven case, the observed size, the physical size stays the same, like RC stays the same, but the observed size is going to decrease over time as the gas mass of the disk drops, which is completely the opposite trend from the viscous model. So we can even have a stronger difference between the two observationally.
Leon, we have a question in the chat from Caitlin Potter, who asks, are you holding m dot or alpha constant in your calculations?
That's a very, very good question. In this case, the setup is slightly different for the wind-driven models. I'm keeping alpha constant in this case. I am not actually looking at the accretion rate for these disks. So that's in contrast to the viscous models. The wind models that I'm showing here, or the wind model that I'm showing here, hasn't been checked against observed accretion rates. So that's one of the things that is different between the two. I can go in more detail afterwards if there's more questions about this. Yeah, in this same figure, let me also include the observations now, which are very interesting to compare them to models to, which is in the end what we wanted to do. I'm showing the observations here slightly different than I showed them before. Right now, what I'm including in both panels is sort of a top-down view of the histogram of sizes in each region to give you, less lines, less confusion, maybe hopefully a more clear picture. As you can see, we talked about this previously. The viscous models can explain the observations in lupus, but they have a hard time explaining the observations in upper SCO. However, compared to the wind model, they seem to be able to sort of match this difference between lupus and upper SCO, lupus being larger overall on average than upper SCO. So that's sort of an argument in favor for these disks being driven by MHD disk winds. However, there's one caveat. These disk wind models, in order to match the two, they also predict that at a younger age, disks should be much larger, which is something that we didn't see. Thinking back to the figure that I showed from the G10 Bergen, it seemed that the younger disks are smaller than what we're seeing at sort of the age of lupus. So in the end, which of the two actually matches the observations? It seems to be both match 2 out of 3. Wind-driven models explain sort of at intermediate and old ages, but do not match the younger class 1, class 0 objects, whereas the viscous disks explain seem to explain both the younger disks and sort of the intermediate age, but then have a problem with the older disks in upper SCO. So that's sort of the state that we're currently at. I think more information is needed to actually break this sort of this degeneracy between the two, or not degeneracy, but the difference between the two models. So with that, I want to take you to the take-home messages from this talk. In terms of dust evolution, we learned that our gas over our dust larger than 4 is a smoking gun for dust evolution. These objects we can really investigate or really find the evolution of the dust. And of the 10 disks that we examined in lupus in more detail, it seems that the ratio is about 50-50. Some of them, like 50%, also need dust evolution to match the observations, and the other 50% can actually be matched within the uncertainties. And for the gas, we found that the gas disk sizes in lupus at least are consistent with viscous evolution, assuming that it started with very small disks and they evolved with a moderate to low amount of turbulence. But this doesn't really match upper SCO. Whereas for the wind-driven model, it seems that it's able to explain both lupus and upper SCO, but it's also making predictions of very large class 1 and class 0 disks, which is also not something that we're finding. So the jury is still out on which of the two is actually driving the evolution. And with that, I would like to thank you for your attention.
All right, thank you so much, Leon. If you have a question for the speaker, you can either use the raise hand feature, or you can put your question in the chat and I will ask it. And I see we have a question from Ninka.
Hi, Leon. Really nice talk. Thank you. So I'm really sorry, but I had missed what you showed about this sizes in early disks. So could you remind me of the tracer that you used there?
Yeah, so it's not something. It's actually not something I'm showed. I think the most that I actually showed here is the. Let's go back to it. Is this plot from Joan, which is sort of the. It seems that the younger disks are smaller than the older disks. The difference being that the younger disks here, what's defined as the size is the transition from going from Keplerian rotation of the disk to infalling material outside of the disk, which is not the same thing that I'm showing in my figures. So,
right, yeah, I was going to bring that up because with that uncertainty of like what is the size of the outer disk, isn't that the easiest way to get around this problem? Like, if we don't really know those sizes, and maybe second, do we actually have good enough statistics on the younger disks and size measurements to compare them directly?
Yeah, no, that's a very good question. I think no, we don't. Currently, we don't.
Okay.
I think really we need to do more work to actually also link in terms of definitions between what we're using in class 0 and class 1s to what we're using in class 2s. Having said that, I mean, the model that I'm showing here, having said that, I think we can be quite confident that just based also on the dust sizes, which we have more for the class 1 and class 0 objects, they're not all 500 AU. So that part at least is clearly not matching up with the model, no matter what definition you're going to use. But it might be that if we go down into the details, that it turns out that we can actually make this all work. So,
okay.
Yeah.
Thank you.
All right. Next question is in the chat from Octavio, who says, very nice talk. How do you compute the dust radial drift? Are you including back reaction? Could be possible that the ratio of our gas to our dust equals 2 can be interpreted as lower dust radial velocities due to back reactions.
Yeah, that's another good question. No, we're not including the back reaction. We're sort of computing, because of the setup of our model, we're computing the dust evolution first, and then we calculate the chemistry. So once we have calculated the dust evolution and we moved over to the chemistry, we are not going to, we didn't go back and then include the back reaction. Could it be lower dust radial velocities? Yeah, that's an interesting point. Maybe it is sort of less efficient drift inwards. The main thing we are thinking currently that it's to sort of explaining the ratio of 2 is that it might be dust traps in the outer disk, and that is sort of both stopping or slowing down the drift of grains inwards, keeping your dust disk large compared to your gas disk. And also, if these rings are optically thick, they could sort of, because we're using 90% of the flux as a definition of size, we might be sort of biasing ourselves because there's an optically thick ring further out that is sort of significantly contributing to the flux at that radius. It sort of might also factor in there. I hope that answered the question.
All right. Next question is from Caitlin.
Hi, yeah, thanks again for the nice talk. I'm wondering if you've thought at all about including infall as a mechanism for changing the size of your disk radii, especially in these models where you're showing very rapid evolution for the first, 10 to the 5 years, when we know that infall is pretty important for these disks.
Yeah, no, that's a very good point, and I agree that especially at these young ages, the model that I have here is not representative of the disks in here. Probably the way to look at these models compared to observations, I would say that t equals 0 is not t equals 0 as that is when the star is formed, but maybe that is when the infall stopped and the disk was able to sort of viscously expand without any influence from outside. But it would be interesting to actually combine infall, sort of add it into the model and see how that would actually change, because I don't know how infall would actually affect viscous evolution from the top
Yeah, I
of
mean,
my head.
there's pretty simple analytic models I think you could use where you would just add a J-dot term into the equations that you showed. And so I think it would not be a large change in your machinery to include something like that. I think in terms of comparing with some of the things that you were showing from Joan, right? It might be an interesting contrast there. So
yeah, that's an interesting idea. Yeah.
All right. Next question is from Diane in the chat, who says, for upper SCO with its nearby OB stars, and if disk photoevaporation is occurring, A, what are the implications for the analysis of the two models? And B, is there data for another association that can be compared to your two modeling approaches for disk evolution, viscous versus disk winds?
Yeah. Let me answer B first, because I wish there was. There's I mean, I've been looking at that, and there's currently there's not really an old region that is as nearby as upper SCO that we can very easily, an old region, that we can compare our models to. Otherwise, that would have been very clear case to go for observations there. If any of you know of a region that I'm sort of forgetting, I would be more than open to actually look into that. So unfortunately, that is going to be difficult, I think. In terms of what would be different from the implications, so there's two effects that you're going to see in the models. One of which I've actually tested. So you're going to have an increased UV field, which will make it easier to dissociate CO in the outer part of the disk. So that will sort of move your CO outer radius inward. But from the tests that I've done, at least for the viscous disks, that doesn't change the size that much. However, if photoevaporation is occurring, it's also changing the surface density in the outer disk, and that is going to be more difficult to sort of analyze. In both cases, it's going to move the observed outer radius inwards. My guess would be that for the viscous disk, that is going to be not as big a difference. Maybe it is, maybe it isn't, but these are quite massive, so I expect you need to photoevaporate quite a bit before you're actually going to see large changes in the disk, compared to the wind model where the surface density is a lot lower. I think it might be very easy with external photoevaporation to just make these disks completely disappear, or at least in terms of observations, completely disappear. So that's sort of my predictions from top of my head, but yeah, it's something that I at some point want to try out and see how right I am with my sort of my guesses about that.
All right. Next question is from Stanley on the graph of the model R-gas versus R-dust for lupus. So he asks, why are there error bars in the vertical direction since these are models and not observations?
Let me get the figure. Yeah, that's a very good question. So there's in here, there's two different definitions of what you consider to be the uncertainty in here. So the ones on the observations, what is put in here as the observed uncertainty is the uncertainty on the total flux sort of included in your measurement where 90% of the flux is. The total flux changes, then the radius where 90% of that flux lies is also changing. So that is the uncertainties on the observations. The uncertainties on the models, what I've done here is because we're worried about the low signal to noise of these observations, is more of a sort of testing the measurement method itself. So what we did is we added noise to our models and then try to measure the size based on those noisy model data. And we did that for a large number of noise realizations, and then sort of made a histogram of sort of the sizes that we would get if these models were observed in sort of noisy conditions that we had in the observations. And then it turns out that for at least 3 of the disks that have these massive error bars, we were getting a large range of sizes that we could potentially measure from our one model, depending on where the noise sort of fluctuations were.
So then the error bars that are being plotted, are those the 1 sigma or the 2 sigma?
Those are the 1 sigma in both
Right.
cases, both for observations as for the ones that I put in my models. Yeah, you can also clearly, yeah, if you look at a case by case for these 10 disks, the ones that have the large error bars are also the ones that have the lowest peak signal to noise of the 12 CO emission.
So then given all of that, the last part of the question is, how do these uncertainties impact the conclusion that 5 of the disks seem to have indications of dust evolution?
That's a good question. I mean, it's still, that means that there's still a possibility that also these disks can be explained with optical depth. It's just that within the uncertainties here, it seems that it's more likely that they need dust evolution. But I can imagine, I mean, we did our best to match the structure of the disk, but there's of course parts of that structure that we do not know. And I can imagine that if you change some of those parameters, then the points on this figure might also change. So it might be possible to, I think it might be possible to get all of these disks to be explained only with optical depth. Is my guess for this.
Okay, good. And then we have some questions from Joan, which will probably be our last ones. So Joan says, really enjoyed your talk. 2 questions. 1, you mentioned the limited signal to noise of some of these protoplanetary disk gas measurements. Would some of your conclusions change if we obtained higher signal to noise ALMA observations of CO emission?
Yeah, I mean, in part, I've answered sort of the first question that I have here. It's interesting, or one thing to note here about the recent paper by Enrico Sanchez is that they actually they did go into that and they made some comparisons, because some of the disks in Lupus also have D-sharp observations, which are much deeper, much higher signal to noise. So they showed that the current observations are within 30% of similar observations that go deeper in terms of gas. So that's something to keep in mind. However, of course, the ones that are in D-sharp and in our survey are the brighter ones. So I hope this is also the case for the other disks, but I'm not completely certain of that.
And then the last question is, when driven accretion depletes the disk mass faster, do disk mass distributions provide any useful constraints on the number of winds?
Yeah, I mean, if we were able to measure the disk mass, then that would be the sort of the second constraint on the evolution, which I think, based on the comparison between the two, would also give you a very strong constraint. The problem is that we currently don't really have a way of measuring the disk mass. We have a good way of measuring this CO, the total amount of CO in the disk, and then it turns out, based on comparing different mass tracers, that something else is happening to the CO. So we need sort of the second part of the puzzle. We need something to also trace the amount of CO underabundance in these disks. If we have both, then we would be able to get we add that to sort of the checks for the evolution.
All right. And with that, we are at the hour. So I would encourage everyone to unmute and thank Leon for a great talk. Thank you all for coming, and see you next week.
Thank you, Leon.